this seminar is very long title. I hope that it does not scare you. This is about the stability analysis of recurrent neural network-based control systems via linear matrix inequalities. And then I will apply this analysis to the design of neural network-based controllers with closed-loop stability guarantees, and also we'll talk about a little bit about how to confer some performance in a database fashion. Okay, so basically, this talk will talk about control systems based on neural networks. Now, well, the most, probably the most widespread type of neural networks is the feed-forward neural networks, which is basically composed of a few layers of neurons which are connected together in a unilateral way. Each neuron basically is an activation function, which is a nonlinear function, commonly a sigmoidal function applied to a linear combination of the inputs. Okay, the parameters A1 and 2, etc., are called weights of the neuron. In this talk, in particular, I will not talk about feedforward neural network-based control systems, but I will talk about recurrent neural networks. Basically, well, roughly speaking, the recurrent neural networks are structures which are very close to the ones to the feedforward neural networks, but they allow for feedback connections between neurons. And well, very generally in this talk, we will describe the evolution of the states of the network according to a discrete time equation. And basically, what we will do in this talk is use them to present the dynamics of some plants, and later the dynamics of control systems. Just like feedforward neural networks, also recurrent neural networks have a number of unknown parameters to be properly learned during the learning phase, and we will generally refer them as the recurrent neural network weights, and here they are called phi, capital Phi. Well, all of us know what are the progresses in neural networks in society. They are widely used in many applications, image classification, speech recognition, bioinformatics, strategic games, and so on. But in this particular talk, I want to focus on the connection between well, the use that we can do of neural networks in the design or analysis of a control system. Well, the connection between neural network and control system exists for many years. It's not something that is related to the last years. We can think about very late works, for example, made by Professor Eduardo Sontag in the 90s. This paper that I'm mentioning here was written in 92, but there are many works that he did in those years about neural networks as system models and controllers. But there are also other works that establish very clearly a connection between neural networks. Well, they can talk about how to use a neural network in the design of control systems, no? And those advancements were spurred by many interesting results about, for example, universal approximation properties of neural networks, and about the possibility of training neural networks using backpropagation algorithms, whose properties were studied exactly in those years, in the late 80s. Why it is worth now going through those results again, or finding new results? Well, of course, now the time is ready for using them in control system. Well, first of all, in view of the fact that new neural network architecture are available, and so there is much more room for research about all the architectures that are studied nowadays. Also, new optimization algorithms have been developed recently that allow for learning these models. Also, some very powerful computing tools are available, like TensorFlow and PyTorch, that allow for very easy learning of a very wide range of neural networks, like data recurrent units, STMs, or also the networks that we are dealing with in this talk. And also, there are new tools in control theory that allow for analysis and design in the linear framework, which is the framework, of course, in which these recurrent neural networks models fall. And so these tools can be used efficiently for control design, for example, as we will do in this talk. So there are many issues remained open, and among which close to stability, safety, and performance, which are definitely worth investigation and in these years. And well, in this talk I will just talk about a very narrow range of results, and I think that there is room for a lot of research on very exciting research this topic. Okay, now we start with a system, with a plant, and we assume that inputs and outputs are available, but the dynamics of this plant, which is assumed to be, let's say, complex and described by a linear model, is not available. But what is available is a batch of input-output data. And so the main assumption is that we devise a suitable model based on recurrent neural networks of the dynamics of this system. The aim now is to design a suitable controller that can confer some stability properties to the control system. Of course, in this framework, also the regulator can be designed as well, in such a way that its model is a recurrent neural network. And as we will see, this is fruitful for many reasons, among which the fact that, well, in order to control a nonlinear system, often a nonlinear controller is more beneficial. But also because if we take as a regulator the same structure of a recurrent neural network that we took as a system, then we can use basically a common framework, a common tool for analyzing and designing analyzing the stability and designing the regulator parameters in such a way to confer input stability properties in this particular case. Okay, so the objective of this talk is to show you how we can design a neural network-based control system directly from data, guarantee closed-loop stability properties, and also, if I have time, to show you how some desired performances can be enforced to the closed-loop system schema using a virtual reference feedback tuning algorithm. On this, well, in the particular case of the networks that we consider in this talk, will be done using linear matrix inequalities, which is a very efficient tool from the numerical point of view, which which is extremely efficient in my opinion. Just let me cast this approach in a framework. What we are basically explaining here is how to adopt a so-called indirect data-based design procedure, which is based on first the definition of the model of a system, and secondly, using the model of the system, define the controller. While there are other approaches which are called direct database design, which allow directly to design the regulator using data. As we will see, in order to guarantee the performance, we will use an hybrid approach where also a direct approach will be used for directly enforcing the performance. But this is something that we will see later on. Okay, let's establish some preliminaries. Of course, I know that in this framework, many of you are much more skilled than me, especially in the technical details of this theory. But I wanted to present a couple of slides presenting incremental input to state stability, which is the main technical tool that I will use, especially for representing the notation that I will use in this talk. So starting from the system model, which is a discrete time model presented up there. Sorry, I need a laser pointer up here. The incremental input state stability property is defined by feeding this model with some initial conditions and with some input sequences. Basically, the point is if we feed the model with two different initial conditions and two different input sequences, then we obtain two different state motions. And if the system enjoys the incremental input state stability property, basically we can bound the difference between the two state motions with a sum of two functions. These two functions basically are, well, one part is a function which depends on the difference between the initial conditions and converges to zero over time. Okay, so the larger the difference between the initial conditions, the larger is this value. But if we proceed over time, this value tends to zero, plus a term which depends on the difference between the two input motions. So just to give you an example, if the two input motions are equal to each other, basically we will see that the different motions that we define using this model will converge to a single one. And on the other hand, if we have different input motions, they do not necessarily converge. Well, in general, they do not converge to each other, but they remain bounded in a region which is defined basically by this K infinity function of the infinity norm of these two sequences. Okay, how to guarantee that a system enjoys delta ISS Lyapunov, delta ISS property? Well, it can be proved by guaranteeing that there exists a delta ISS Lyapunov function for the system. Okay, basically, delta ISS Lyapunov function, well, is a function of the two different state evolutions. Okay, which can be upper and lower bounded by K infinity functions of the difference between the state, and whose evolution can be bounded by minus a K infinity function of the difference between the states plus a K function of the difference between the inputs which are applied at distance K. Okay, basically, if you think about ISS Lyapunov function, this is very, very similar, but instead of considering absolute values of the states, we use basically differences between the states and the inputs at any time. Okay, so basically the main tool that we will use to confer delta ISS property will be to enforce the existence of a Lyapunov function for the system or for the control system that we will analyze. Okay, so we start from the control system. Why delta ISS is useful to be guaranteed in this particular case? Well, the main point is that if the system enjoys delta ISS Lyapunov function, of course, with respect to the input, which is now the reference to the control system, basically we will have convergence of the output to a certain point effectively of the initial condition of the system when we control. Lyapunov function is very important because it guarantees some robustness with respect to disturbances acting on the system. So to bounded disturbances, we have bounded effect. those disturbances on the state, the output variables that we are measuring. Okay, now what kind of recurrent neural network consider in this talk? Now, this is a very simple class. If I have to be honest, recently we are greatly extending the results to classes which are a little bit more much more informative than this class. But the starting point of our research was this class, and so I think it would be clear to present the results here by starting from this rather simple class instead of considering more complicated structures which make everything more complicated. So I will start from this class, which is a very simple single layer recurrent neural network where we have an activation function that we call f, which is applied to a linear combination of states and input. Okay, this is a linear function of state and input, and the output is linear. Now, the nonlinear function f, the function f is composed of functions that must be applied element-wise to the elements of the vector that is inside here. But we don't consider just nonlinear function. We may consider also some identity functions which represent the fact that some of the lines here of this function may be linear. Okay, so we are not excluding a priori some linearities in the model. Okay. The main property that the function f should satisfy is that normally f is a sigmoid function, and in this particular case we ask the function to be Lipschitz continuous, and in particular we assume that a global Lipschitz constant exists and is defined as LPI for each element of this nonlinear part. Okay, so we call LP1, LP2 up to LP nu the Lipschitz constants of these components, while of course the identity function that allows to define the linear parts of this model are of course equal to 1. Okay, we collect all these Lipschitz constants into a matrix LP, which is a diagonal matrix just containing all these constants here. Okay, now the main result that I will show you also the sketch of the proof in a few minutes is this one. We can prove that this model here is a delta ISS if there exists basically a matrix P that allows to solve this Lyapunov inequality here. Basically, the Lyapunov inequality applies to LP, which is the matrix of Lipschitz constants, times A, which is the transition matrix of the linear part. Okay. Now, of course, there is a trick here because not all the definite positive matrices P allow to prove the delta ISS property of these nonlinear systems, but only structured ones. In particular, the first, the matrix P should be a block diagonal, where the first part here must be purely diagonal, and the second part does not necessarily have a specific structure. Okay, so every time we have a nonlinearity, the corresponding Lyapunov function must enjoy some diagonality, while for the linear parts we allow for a more free structure of the Lyapunov function matrix. Okay, Lyapunov inequality matrix. Okay, so this is the main condition that we will satisfy for delta ISS of the system, but also we will apply for the control system design. And so this is the main condition that on which we will focus during our talk. In order to show how to prove this result, I will show you that basically this candidate delta ISS Lyapunov function is indeed a delta ISS Lyapunov function. Basically, we define V as XA minus XB transpose B XA minus XB. Okay, so basically how we will define a Lyapunov function also in the linear case with the quadratic one and very standard. Now, of course, I will show you that it enjoys the two main properties that allow us to guarantee that it is indeed a Lyapunov function. Let's start from the first one. Well, of course, since P is a definite positive matrix, we can upper bound V with using the minimal and maximal eigenvalues of matrix P, because it's asymmetric and positive. Okay, so this is a totally standard thing. Well, I think that the most insightful and interesting part, of course, is the second one. We start by representing the evolution of the difference between the states, XA and XP, by just applying, the evolution of state XA is computed by just applying function f to A times XA plus B times UA. We call this VA for brevity, minus f applied to VB, sorry, which is A XB times B UB. Okay. Now, the main trick here is to add and remove this part here, which is the matrix of Lipschitz constants times the difference between VA and VB. We remove it and we add it here, and we call this term here delta, okay, while this is LP. Now, if we write the expression of the Lyapunov or the candidate Lyapunov function at time k plus 1, of course, we have this transpose plus times P times this expression, okay? Now, if you look at what I have written here, basically this is delta V transpose LP, P, LP, delta V, which comes from here. Then we have delta transpose P delta, which comes from here, plus 2 times delta V transpose LP transpose. Recall that LP transpose is LP because LP is diagonal, P times delta. Now, we can collect here in the right delta and obtain this part times the sum of delta plus 2 delta V transpose LP, transpose P delta. Now, let's focus on this function, because the main result that we obtain is obtained by just analyzing that function. So let's rewrite it by clearly expressing these two terms, delta and delta plus 2 times LP delta V. Well, delta, as I told you, is the difference between the functions applied to VA and the VB minus the Lipschitz constant matrix times the difference between VA and VB. While the first term here, by its definition, is the difference between the functions plus LP. Okay. Now the point is for the terms of f which are linear, so the last terms, this difference here turns out to be 0. Okay, because VA minus VB is exactly equal to LP times VA minus VB. So for the linear terms, this part disappears. And what remains in this product is the part related to the nonlinear functions, the first nonlinear functions. Okay. Now, the point is, and here comes the important part about the diagonality of P nu. Okay, because if P nu is diagonal, basically we can write this product as a sum of the products between the elements of these vectors times the elements of the diagonal matrix P nu. Okay. So if you look more closely to this product, you can see that the first part is the same into the 2 parentheses. And the second part is the same with a different sign. So basically we can write this part as the sum of terms which are Fi applied to Va minus Fi applied to Vb squared minus the Lipschitz constant squared times the difference between the two values of V. Okay, and now we can use the Lipschitz continuity of function f to prove that all these terms are smaller or equal than 0. Of course, the sum of these the weighted sum of these terms, weighted by parameters pi, p nu I, which are all positive, is also smaller or equal than 0. Okay, so this is the main part of the proof. So basically, the structure of the matrix P allows us to prove that this part is negative. And so if we go back to the previous slide, we realize that this part is negative in view of the definite positiveness of matrix P and of its structure. And so the difference between V, the candidate Lyapunov function at time k plus 1, and the candidate Lyapunov function at time k, it can be written in this way. Basically, if you look closely on how we define delta V, this is the difference of the Lyapunov function in a purely linear case. Okay, so furthermore, the matrix LP times A is sure stable in view of the fact that this Lyapunov inequality is fulfilled with a P which is definitely positive. So in order to prove that this is indeed a delta S Lyapunov function, we can use the same tools that we use in a linear case. So I will not go through them again. But the point is really this. We prove that what we have here is smaller or equal than 0. And so we use linear tools basically to prove the same tools that we apply in the linear case to prove the decreasing property of the function V. Okay, and so basically we can prove that V at time k plus 1 minus V at time k can be upper bounded by minus a constant, positive constant xi times the difference between the state, plus lambda, which is a positive constant, times the difference between the input, which is exactly what we required for V to be a delta SS Lyapunov function, and so we can prove the delta SS property of system S. Okay, so at the end of the game, we have to solve a Lyapunov inequality, just like in the linear case, but imposing a particular structure to matrix P. Okay, this is the trick that we apply. Okay, now that we established a analysis condition for simple systems, we use it for the design of controllers where the system and possibly the controller itself are recurrent linear networks. Okay, so well, basically the main trick will be this: we start with a model which is identified from data, and we assume that a recurrent neural network model of this type well represents the system dynamics. And what we do is design a regulator and possibly also a compensator, which allows to improve the performance, which are of the same recurrent neural network class that we have considered so far in the analysis part. Okay, so if we plug together the states of the system, the regulator, and of the compensator in a single vector X, we can easily see that the overall control system dynamics can be described by a model which is exactly a model that falls into the class that we have considered so far. So the class of recurrent neural networks that we are studying there. Okay, so the point is where, of course, the input here is the reference value for Y. So the point here is that we will confer input to state stability, if possible, to this model, and this, of course, will be used to provide very good performances, well, good performances to to the control system. Okay, so again, just to recap, S, the model of S is given by the data. So the model of S does not present any unknown parameter because we have already identified them in the learning phase. While here we have a regulator and possibly a compensator, which can be represented, can represent dynamic, the dynamic nonlinear regulators, static nonlinear regulators, or even dynamic and static linear, not dynamic, even static linear regulators, if we just remove this part here. Okay, so the main point is that in any case we can represent the closed loop system dynamics in this way and use the result that I presented so far to confer stability properties. Okay, so just to be clear, that here we have a matrix A, and by just verifying this Lyapunov inequality, we can verify the stability of the system. Of course, this is not just an analysis problem in general, it's a design problem. So provided that, which is not guaranteed for any structure, but in many cases it will, as I will show you in the subsequent slides. If we can define some free parameters of the controller and of the compensator such that we can write the evolution matrix A as F plus GK or F plus H times L, where L and G comes from the model, then we can cast everything into a linear matrix inequality problem, which can be easily solved, allowing to obtain a very lightweight design problem. Okay, now there are many questions. Okay, so I'm listing just some of them here, and I will try to cover them in the next 20 minutes. So, how to design controllers for different configurations? Of course, if we just use the tool that I presented so far, we can just confer some stability properties, which may not be enough, especially in many cases. So we would like to know also how to enforce some performance, possibly in a database fashion, because we are assuming to be in a database control design scenario. The other research questions are about the robustness, because maybe the learning phase does not provide just a unique model, but a set of possible models which could represent the system dynamics. And then I will tackle also the feasibility issues, which are strongly related to the global condition that we are considering now for the ISS. Okay, let's consider, the case we want to design a regulator which falls in the class of eco-state networks. Okay, why we use eco-state networks? Because basically in eco-state networks, this is the regulator based on eco-state network. In eco-state networks, we have a lot of parameters which are represented by matrices WX, WE, and WU. But some of these parameters may be set as hyperparameters before the design phase. And in particular, in this case, we set these three matrices here before the design phase. So they are hyperparameters. Normally, this is also what happens when you learn eco-state networks. Okay, I am not delving into details how to set them because it's not important in this phase. And we use just KR here as free design parameters. And what I will show you that we can use the Lyapunov inequality that I derived so far in order to design the parameter K in order to confer delta ISS to the control system. Okay. Well, the point is the control system itself can be indeed written in the form that I presented so far. And in order to do this, we just have to plug these equations together and obtain a state space form which is of the same type that I considered before. So I take the two state equations on XR and XS, and what I first do is I replace E with R minus CX, which is R minus the output of the system, and then I replace U of the system, the input of the system, as the output of the regulator, so K times XR. Okay. If I do this, I can clearly show that the evolution of the overall state of the network can be written as a function of the overall state of the network times a term which represents the influence of the input R on the states. Okay. So basically, we have this equation here, no? Well, in order to, well, this is not exactly true, because in order to write F in the format that we like, I like for writing down in a simple form the Lyapunov inequality. Normally we have the linear part at the end, but if we do this, we don't have necessarily have the linear part at the end. Well, let's say, under the assumption that Xi is all non-linear, this is true. Okay, we have all non-linearities here, and the last part is consists of the linearities of just Fs. So it's nice. Okay, sorry for this. And so we just have to write the function in this way, and basically the matrix A, which represents the evolution of the state, which comes from the equations that I've written before, can be indeed written as A0 plus B0 times K. Okay, here K has a specific structure, but we don't really care, because the structure of a gain matrix normally can be conferred by, for example, tools like YALMIP. So we can specify a priori the structure of the gain matrix, and then we will obtain a design problem that will provide a gain matrix which has the structure that we want. Okay. So basically, the main point here is that in order to confer delta ISS property to the closed loop system, we have to solve the Lyapunov inequality where the matrix A is this one. Okay, so basically, this is the main point. We have to verify this. If you read it as it is now, matrix P and matrix K are both free variables of the matrix inequality problem. But I will show you in a few seconds that we can cast this problem as a linear matrix inequality one. Okay, so well, we want to verify this using very standard tools, by the way. So I could skip this part, but just to show you all the details, I will do it, at least for the regulator. So basically, the first thing is that I take this matrix, which is the matrix of the Lipschitz constants, inside of the parentheses. So I just keep P here alone, and here, as you can see, I have LP pre-multiplying A0 and B0. Okay. Then I define Q, which will be my real optimization variable in the LMI problem, as the inverse of P. Okay. So I just replace P with the inverse of P, and I pre and post multiply the inequality by Q. Well, now what I do is bring Q inside of the parentheses and obtain this equivalent inequality. Okay. The main trick here of the linear matrix inequality is that this product between free variables, which are now K and Q, will be defined as a unique free variable that we call H. Okay, the point is we define H as a new free variable, and then we will be able to retrieve K from H and Q. No? And the main point, this is very important, because since we want the K which is structured, we need to define a structured H that allows us to define a properly structured K. But if we structure H in this way and Q in the same way as we want P to be structured, we will obtain K structure as we desire, and also P structure as we desire. So we will be able to fulfill the delta S inequality that we need. Okay, this is the main point. So basically, we use the Schur complement to transform this inequality into this, and this is our linear matrix inequality that allows us to confer delta ISS to the system. Okay. Now, in the next slides, I want to simplify a little bit the setting to show you also the part related to the performance. In order to simplify the setting, I use a state feedback static controller, okay, which allows me to simplify a little bit the equations. Okay, so instead of considering a neural network here as a controller, I just use a gain, a static gain. Okay, of course, in order to guarantee some tracking properties, I have to define a reference R, but here I used as a reference to the state for the state and for the input input and state that allow me to solve this static equation, which comes from the dynamic equation. Of course, as you can clearly see, not all references can be tracked in general because fs is a bounded function, so not all the references can be tracked. But we assume that x bar, u bar is indeed a solution to this equation. Okay, so basically this is the control law that we apply in this case, and I will show you that similarly to what I did before, we can define a design problem allowing to define K that confers input state stability to our system. Okay, so if I plug this control law into the system, what I obtain is exactly this equation. By simply managing this, I obtain the equation where the transition matrix becomes A plus BK. Okay, and here I have some inputs that remain here that allow to track the reference. Okay, now the main point is to realize that this state evolution is exactly the equation in steady state. Okay, where, of course, here I'm considering the steady state XR bar instead of X. But because the point here is that if I start with X as a steady state, basically I remain there. So if this equation enjoys delta input to state stability, that automatically implies that XS will converge to the steady state, no? Because if I change the initial condition, I will converge to the same solution that I obtained by the static equation, okay? And so basically the point here is guaranteeing static performance and stability just by solving my Lyapunov inequality, my particular Lyapunov inequality applied to this matrix here, AS plus BSK. Okay, and of course, as I told you, this will guarantee that XS will converge to the state that corresponds to the reference. Okay, of course, this is a very, very similar problem to the one before, so I'm not devoting time to show you that this can be cast as a very simple linear matrix inequality problem. Okay. Now, there are two questions that arise here when we see these slides. The first question is, okay, but here S is a recurrent neural network, so it's not a physical model. So the state of the recurrent neural network does not correspond to any physical variable. So I cannot assume that XS is measurable. And of course, this is totally true. And for solving this problem, I will show you that a simple observer can be designed. And the second issue is, okay, but in order to, when I change a set point, I should automatically know a UR bar and XR bar that allow me to track that change in set point. So if I want to avoid an automatic computation of the set points, what can I do? And of course, you can do it by adding an integrator to the control system, exactly like you do in the linear case. Okay, so, well, let's see how we can design an observer. Well, of course, an observer is designed by just replicating the system equation and adding a correction term, which depends on the residual, so the difference between the actual output and the estimated output obtained using x hat s, so the estimated state in the output equation. Okay. Now, we can rewrite, well, of course, we can write it as AS minus LCS, where L is the observer gain, plus something, okay? Why did I rewrote the system equation? Because I want to show you a very simple thing, that we can write also the system equation as A minus LC times something. And by the way, this something is exactly the same that we have in the observer. And why do I say this? Because I want to point out that if, as initial condition of the observer, I take the initial condition of the state, I automatically have that the observer state is equal to the state of the system. This allows us to say that provided that the system enjoys delta input to state stability, if we start with an initial condition of the observer in a different point, the trajectory of x hat will necessarily converge to the trajectory of the state, okay, by definition of the delta ISS property, okay? And this allows us to prove that I have convergence of the observer error to 0. Now, the main point is, and this can be conferred by applying our Lyapunov inequality, particular Lyapunov inequality, to A minus LC. Okay. Now, I don't want to devote time to show you that also this can be written down as a linear matrix inequality. You can see the details on the slide. I will share them with you. Now, the main point is, okay, I'm giving as a feedback the estimated state, but I can write the estimated state as XS minus the observer error, okay? But the observer error goes to 0. So if you write the system equation, when you use the same controller as before, but where X hat appears, you can see that the same equation can be written, okay, but where we have a further perturbation to the state equation, which is given by Bs times the observer error. But since we are able to confer delta ISS to this system through our Lyapunov equation applied to this matrix here, of course, when this vanishing disturbance goes to 0, this allows us to prove also that XS tends to the set point. Okay, so we apply a sort of separation principle because the observer error appears as a disturbance in a delta ISS equation, delta ISS system equation. Okay, the other issue is, okay, what if I don't know the steady state? We can use an integrator, okay? Well, basically here the point is we are adding an integrator here that integrates the observer error, and we provide the estimated states to the gain, okay? We can very easily prove, using the same argument that we apply in the linear case, that the only possible steady state for this control system is the one corresponding to having a control error R minus ys equal to 0, okay? Sorry. And so this allows us to say that if we guarantee stability properties to the control system, the stability property will lead us to have a convergence of ys to the reference, okay? Now, the control that we apply here is U equal to K, well, K times a vector composed of both xs and v. Okay, so we will have a gain that multiplies the state xs and another gain that multiplies the integrated error that we call v. Okay, now the trick here is the same, so it's not really important that I delve into details, but the point is I put the equation of the integrator and of the state evolution together by, of course, using kx and kv in the equations representing the input here. And at the end of the game, I will obtain a state evolution, which is exactly represented by our recurrent neural network model, okay? Where the state, instead of just being composed by xs, is composed by xs and v together. So the state of the system plus the state of the integrator. F has the same structure that we needed. So the first entries are nonlinear, and the last entries are linear because the entries of this integrator equation are linear. And so at the end of the game, we obtain an evolution matrix, a transition matrix, which is written as A0 plus B0K. So here, again, the point is to use the same LMI that we used before to design the gains Kx and Kv, which are collected together in a gain matrix K. Okay, so we use exactly the same tools. Now, the next point is, how do I guarantee some performance? Because here, as you can see, I obtain some conditions which are, let's say, somehow flexible in the sense that there is no one solution, but there is a plethora of solutions. If the LMI is feasible, we have a plethora of different solutions, but there is no way to decide which solution is the one that allows us to confer some performance. No. Furthermore, in general, for linear control system, it's not very easy to find standard tools for guaranteeing performance. And plus, we are in a database framework. So what I'm suggesting here is, why don't we use directly the data to confer some performance? And the approach that I'm suggesting is the use of virtual reference feedback tuning, which is quite efficient, especially in some particular cases that we have tested, but I'm not showing the result here. So the point is this. Okay, if we take this control system, no, and we represent it as a system with R as input and Y as output, this is a block of this type. Okay, we have data which are related to the plant, and the idea is to tune the free parameter, in this case K, the gain K, in such a way that the model of this closed system is as close as possible to a reference model mref that I'm predefining. Okay, the idea of virtual reference feedback tuning is very simple. Okay, we have Y, and if the system behaves as we want, we can invert the model ref to obtain what will be the virtual reference R in such a way that with the specific reference model that we want to impose, Y behaves as the data that we have. Okay, so the point is, if we had an optimally tuned controller, and by the way, a controller which has the structure that we need, because not all controllers will allow us to get those results, if we have this as output, the input will be the inverse of the reference model times the data that we have. Okay, and we put it here. Then, using this data and the output data, we compute the virtual control error. By integrating the virtual control error, we obtain the integrated virtual control error. And these are data, because once we know this, we can compute this by inverting the reference model, we can compute this, and we can compute this. Now, also US are data, and also XS can be defined as the data, because we just obtain them by feeding the observer with input and output data. So if you just focus on this part, you can see that we want to tune K in such a way that if properly fed by data x hat and data v tilde, the output is equal to the data that we have. So if you just write it in equation form, we can write it in this way. We want to tune k in such a way that k times some data that we have or on some time instance is exactly equal to some data that we have. Of course, this is not possible for in general, because the equality is practically impossible to have, at least because we have some noise on the data. But we can cast this as a least square problem, no? Because what we can do is let's minimize the cost function that allows to minimize the difference between this and this part. Okay, and we can see that this is a least square problem where k is an unknown. But of course, in view of the fact that the controller may not be the optimal one that allows to obtain the reference model, in view of noise and other features, this may turn out to be even an unstable controller, no? And so, what is better to do? Let me skip some details. What is better to do is to minimize k, but keeping in mind that we have to guarantee the stability. And the stability, of course, is guaranteed by the linear matrix inequality that I derived before. Okay. Well, this thing is a little bit tricky because the linear matrix inequality does not have k as a free variable, but h, which is the product, is the product of k times q. So this makes everything nonlinear. Unfortunately, I don't have much time, so I will skip these details, but I will show you that with some approximation, so we can bring this problem into, approximate this problem with a problem which is in Q and H. So in this way, we can not only guarantee the stability, which is enforced by this inequality here, but also guarantee performance by properly minimizing the cost function that you retrieve thanks to the cost function that we define using the virtual reference feedback tube approach. Yeah, lastly, I want just to talk about robustness, because of course, as you may imagine, the model of the system that we derived by learning may be uncertain. Okay, so what can be proposed is, instead of using a nominal model of the system in our LMI, we can, using the some set membership tools, so we can define, instead of a nominal model, a set of models of which the real one is a linear combination. Okay, so basically what can be done in order to confer stability is not solve the LMI for a nominal model that we don't know, but we solve the LMI for the vertices of some polytopes containing the limit models, model parameters, and by solving this LMI, which allows to confer stability to the limit models, of course we can confer stability to all the models that can be described as linear combinations of those models. And the identification of these limit models can be done using very standard set membership tools. Okay, just a few words also on the feasibility. So I think that the main problem here is, is it this design problem always is feasible or not? Well, of course not. Okay, in view of many things. Okay, first of all, this comes from the fact that the condition that we have derived is conservative. Okay, and one of the reasons of conservativity is the fact that we are solving this feasibility problem for functions that have the same ellipsis constant. So we are not focusing on the specific nonlinearity that we are considering. So of course, we guarantee stability, but we are not just focusing on the specific model that we have, but on all models that whose linearity can be described in the same way. So of course, it brings a lot of conservativity in our design problem. And the second thing is that if you have noticed, we are guaranteeing a global stability property, but especially when dealing with bounded nonlinearities, global stability properties cannot always be conferred. This is just an example. Assume that in view of the structure, so the sigmoidal structure of the system, ys cannot take values which are greater than a certain value y max. Okay, and we ask for a reference which is greater than that. Of course, we cannot have global stability, because if we give a reference which is greater than the maximum value of y bar, we have an integrator which continues integrating that variable. So inherently in our LMI problem, we have the impossibility of get feasibility when this variable is bounded. Okay, so if you test this inequality, you will see that you have to insert some linearities, especially because otherwise you can never get the feasibility. This is a structural thing. And so what we are doing currently with some collaborators is studying local or regional stability concept, because only in that way we can define some specific stability enforcing LMIs, but which can apply to any type of linearities of this type, and not only to specific structure where we enforce a linearity just for guaranteeing that the output can be possibly unbounded. Okay. Just to draw some conclusion before to leave the floor for any questions, I just wanted to point out some of the take-home messages of this talk. Well, first of all, I pointed out that if possible, the incremental input stability property is a very, very interesting property to be conferred to the control systems. And for some classes of recurrent neural networks, this is a property that can be conferred even using some linear matrix inequalities. There are ways to confer also robustness, to confer some performance even directly from the data. Okay, one of the main points here is that we don't always have feasibility. So the next step of the research that we are currently studying is exactly to derive some conditions that guarantee local stability instead of global one, because the global one brings too conservative linear matrix inequalities. These are some papers that we wrote on this topic. This topic is well, not following exactly the first paper, but is let's say a simplified version of this paper. So I presented the main concept of this paper in this talk, but we developed this theory further on, and in particular, we developed some local or regional stability conditions, and we use also these conditions to derive auxiliary control laws for MPC, and so we confer some performance not using virtual reference feed tuning in these works, but directly using a model predictive control whose soundness is guaranteed by the conditions that I've talked about in this talk.